as we said, the perception test has been proposed, done by a bunch of large number of researchers. You see some of them in the picture. You see them in the picture, and you'll see some of them presenting in the next session. Next. A quick reminder: we covered in the first part the overview. We shared, if you've just joined us, you can look in the chat to the link to try out the perception test yourself. We also covered the link between the current perception test and current existing benchmarks, which we claim to be test sets rather than tests. In this second part, we'll dig into the annotations and the baselines and next steps. Next. In the annotations, we will be talking about the 6 types of annotations that have been collected with videos collected for the perception test, starting with the object tracks, then point tracks. Then Adria will be covering both the action segments and sound segments. Then we go back to Viorica to cover the multiple choice video question answering and the grounded video question answering. Next. With that, we'll start with Ankush, who will cover the object tracking.
Right, so I had some difficulties unmuting myself. Thank you so much, Dima, for the introduction. Okay, so this is a deep dive into the object tracking aspect and objects in the perception test. Okay, so let's talk about objects. It's been known that infants sort of form very concrete representations of objects early on. So they perceive objects as complete, connected, solid bodies, which persist over time. And it has been argued that machine perception could also sort of build on these concepts or object-like things where you reason about parts and subparts. So sort of this flexible recombination of objects or concepts and their attributes and affordances will perhaps forms the foundation of perception, at least in humans and maybe also in machines. So with that in mind, we know that the main benchmarks, the key benchmarks in our community sort of are built on top of objects. So starting from object classification to detection, segmentation, tracking, pose estimation, 3D reconstruction, and so on. The fundamental annotation is that of objects. So either there's a predefined list of object categories that you want to train your model to classify into, or you want to find a particular set of objects in the image or video, or you want to segment those. But the essential key annotation are these objects and the interrelationships. So these early benchmarks sort of are focusing them on objects themselves, but there are also now more recent benchmarks which go beyond objects and talk about object relationships and their attributes. For example, in the visual genome dataset, we have annotations for objects and also how they interact with each other and humans. And action genome further takes a few steps further and extends this to spatiotemporal scene graphs, which are embedded in videos. So you would have annotations for humans and various different objects, the attributes and relationships. With this in mind, even for perception test, we started with objects as our root annotation. So in total, we have about 190,000 object tracks. So these are axis-aligned bounding boxes annotated at 1 FPS for most of the objects in the video. Just for reference, there are about 12,000 videos. And these annotations are then form like the bedrock on which other annotations like points are done. So the annotators were asked to label points within the object. So we know if we are given a point track, we know which object it belongs to. And points can be seen as more spatially precise targets for tracking. Second sort of annotation we have are actions. So in addition to the standard action classification annotations where you're just given the category for actions, here we have attached with action labels, also which objects are involved in those actions. And there are about 60,000 objects which are involved in various actions in the data set. And then we also have sound labels, where we have the category of the kind of sound it is, but also annotated the participating objects for each of those sounds. So we know which objects are involved in causing or producing the specific sound. And there are about 63,000 objects which are involved in these annotations. And finally, for grounded VQA, we know as the answers are sort of embedded in objects. So the answers to the questions are not just text-based, but also where those objects occur. And these are embedded in the object tracks that we have. And there are about 9,000 objects that are involved in the grounded VQA questions. Okay, so let's take a look at some of our object annotations. Our objects are annotated at 1 FPS, and this is what we're showing here. You can see that the objects are annotated even through occlusion sometimes. So for example, this object number 8, which is the film, as it moves and as it is occluded, it's still annotated. Here's an example of annotations of objects and points. I'm not sure if you can see this. I think there's an issue with the video loading. I'll just give it a few seconds for it to load. Okay, there we go. Display this. Right. I'm not sure if you see it playing, but essentially what it should show are object boxes with points annotated on those objects which move along with the object, and objects that belong to the same object are colored in the same color. So we have that relationship also annotated in our data set. Next is this example video where we're showing annotations of actions. So in addition to the action categories, we know which sort of objects are involved in those actions. So here you can see this ball rolling down the incline. And for that action, which is labeled launching something, we have the ball also annotated there. And the book on which this incline is placed. Okay. Right. I think there's again some issue with the video, so I'm gonna try to go back and forth, see if this loads. Okay. So right. So unfortunately, there's some issue with playing videos. But what this video is supposed to show is the annotations we have for sounds. So in this video, the person takes the vegetable and hits it against the vessel that you see, so some crockery on the table, and that produces a sound, and that's labeled in the data set. And along with that sound label, we have attached object tracks, and we know exactly which objects produce that sound. Okay, so how did we go about collecting this annotation? So here's an example of visualization of our annotation interface. Here you can see the annotator drawing the bounding box on the head of this person at 1 FPS. The key difference that we had in our data collection as opposed to other existing tracking benchmarks is we asked the annotators to type in the object class and names in free-form text. So we don't have a predefined list of object categories that they have to label. They were just loosely asked to label some 10 objects per video, which are moving or involved in action and are prominent. And that resulted in this short strings of object descriptions. For example, red bag or blue bottle, if they're there in the video. And for these 100 90,000 object tracks, there were about 5,000 unique object strings that were harvested from the annotators. And this plot is showing the frequency for various unique words within those text descriptions. So as is common in our video content, like humans are pretty prominent. Humans show up pretty prominently, but there's a long, long tail of a lot of objects. In fact, if we compare the distribution of objects that we have with existing object tracking data sets, we have the largest number of different classes or unique object names. So this is a list, this is a comparison against existing single object and multi-object tracking data sets. So you notice that our data set is labeled with multiple object tracks per video, and there's a large set of object categories in our data set. Also note that most of the object tracking data sets are just for that specific purpose of tracking. This perception test has a dense set of annotations. So in addition to object tracks, you have other associated annotations for like point tracking, sound recognition, action recognition, and so on. Right. So let's talk about a few challenges that we came across when annotating objects in the perception test. So the standard definition of this single object tracking task assumes that the first frame in which the object appears is given as input to your algorithm. But we found that for approximately 20% of the object tracks, the first frame itself was not informative. So you can imagine an object entering the frame, and as it enters, the very first instance, the very first frame where it enters, only a few pixels would be visible. And if you just take that as the initial template of the object, that's not very good. It's not very informative. So we had to resolve this challenge by coming up with some heuristics that would give us a good initial box to start tracking from. So one of the things that we did was pick a box or pick a frame where the object is away from the frame boundaries. And the second sort of heuristic we used was run a baseline tracker and then pick as the initial frame the frame from which it can track successfully for the next 2 seconds. So, okay, so the second set of challenges that we came across were in the ambiguity of the tracking task. So the tracking task, the single object tracking assumes that given a template, the object doesn't split, or it's always just this one monolithic thing, but that's not true. For example, when you're chopping vegetables or salad, or you're opening some boxes, it sort of splits into 2, or something breaking into subparts. The similar sort of issues sort of come up with liquids when you sort of pour from one container to the other. How do you label the liquid in that container? Or if you have an egg and you break it. So if you start with the box around the egg, and after the break event, you have sort of 3 things. You have like 2 pieces of the eggshell and the egg white. So how do you label it? And the key challenge is, how do you get the raters to do this consistently? The other key challenge was transparent containers. So if an object sort of gets contained in another transparent container, would you consider that occluded or not? Would you then stop tracking, or should you start a new track from there? So all of these are inherent ambiguities, reflect inherent ambiguity in the single object tracking task, and were challenges for us. Currently, we're making an effort to sort of exclude these tracks from evaluation. So the annotations will be there, but not used in the evaluation. But as a community, we need to come up with better task definitions and also models. So right now, single object tracking models cannot split a track or start new tracks for a given single track. So we need to have a deep rethink about this problem definition and our models. So this is supposed to be a visualization again of Okay. Right. I'm not sure if you can see the video moving, but this is supposed to. You see it? Okay, great, awesome. So this is, as you can see, an egg being broken. As I was discussing, you start with a box around the egg, and then it gets split into three things, and then it's unclear after the splitting, after the opening of the egg, which part you should track. And different annotators do this differently, and that was a challenge for us. The second example showing how a particular, okay, hopefully you can see this video as well. What if not, then what this video is supposed to show is how the annotators dealt with the fact that the lettuce will be split in the future. So what they did was they watched the entire video, went back, and right from the start, they created multiple object tracks. So if a piece of lettuce was to be broken into two, they would start with two tracks, and then as it was broken, then the two tracks would be maintained. But different annotators will do this differently. So this is a challenge for us. And so right now, as I said, what we're doing is identifying these and excluding them from evaluation. Okay. See if I can play this video. Not sure again if you can actually see this. Okay, but right. So this video is supposed to show transparent glasses interacting, so one on top, one in front of the other, and it's unclear what is the extent of these glass, right? So one could argue that since it's occluded by another transparent object, it ends at the boundary of the occluding object. One could say it's actually visible. So there's inherent ambiguity in how you specify the extents of the object, and these this ambiguity is there in the data. Okay, so I'll next talk about how we define the object tracking task. It's the standard definition used popularly in the community, where the input to the algorithm is the initial box or initial object template, plus all the frames from the video, and the algorithm is expected to return all the boxes in the video frames. As I said, we had some issues with with using the very first frame as the initial box. We found that for 10% of the object tracks, we had to use the second frame, which gave us a better object template. And for another 10%, we had to use the third frame, which again was a better template rather than the first two. Okay, and this is how we evaluate the object tracking performance. So it's very simple. We take the ground truth boxes over time, and we take the overlap with the predicted boxes and just take a simple average. This is also called average overlap in the community, and has been shown to be a simple metric which has strong correlations with other more complex tracking metrics. That's the reason why we chose this for us. Okay, so in order to benchmark and assess the quality and difficulty of a dataset, we implemented the simple tracker, which is the SIAM-FC tracker. So the SIAM-FC tracker is a template-based tracker. What that means is given the initial box, it extracts features from a pre-trained ResNet. ResNet is trained on ImageNet. And then for any given future frame in which we need to localize and find that object, we do a simple cross correlation and find the peak for locating that object. The positive aspects of why we chose this was that it's class agnostic. You can just get ResNet features for anything, and it's not specifically, it doesn't require training on the specific data set. So we sort of use it in this zero-shot manner or one-shot manner, where due to this template that is given as input. Also, SIAM-FC is a simple method which achieves good performance in a number of single object tracking benchmarks, as compared to other very complex methods. All right, so just to dive a bit more deeply into the implementation. So we follow Unitrack's implementation of CMFC. Unitrack is this recent work which looks at various ways to use self-supervised features and other features to do a lot of ton of tracking tasks. And we just focus on the single object tracking task here. And down below here, you can see the performance of the single object tracker on the OTV benchmark. So it's looks pretty good. One sort of implementation detail is that we fixed the template, we resized the template that we use to a 520 by 550 window by preserving the aspect ratio. And we do a multi-scale search over 3 scales. There's also a prior on that's used in the algorithm, which prefers that the object doesn't move. So there's a cost on moving too far from the last location of the object. Okay, so here are the results. So the results are broken by which objects are we looking at. So as I said, the objects are involved in actions and sounds and grounded VQA. The first thing to notice is that about 65% of all object tracks that we have are static, or they don't move much. So you can see that in this top left column with the 68 number, where this with all objects and with camera not moving, the performance is reaching this 68% IOU. Whereas if you compare and contrast that against objects involved in actions, that is the second row with a moving camera, that is second row, second column, the 46% IOU, you can see the large drop. So what this is showing is that the tracker is struggling on moving objects, and also that a large fraction of the object tracks that we have, which is approximately 65% in the data set, are static or not moving very much. We found that was looking at the output, we found that when the camera pans or the object gets occluded, that causes like extreme failures. That's extremely challenging for the tracker. Also, small sized objects which move very quickly also put up a difficult task for the tracker. And in this experiment, we're doing a simple comparison against this simple baseline of where we just take the initial box as the prediction for the entire video. And you can see that the CMFC barely improves on it, but barely, just barely. So it's worse for static objects. That's obvious, because like static baseline is always going to do better. But for moving objects, CMFC does slightly better. Note that we're using, we initialize the CMFC tracker only once, but we don't reinitialize it during the video, as is common in the community. So it's only given a chance to track just once, starting from the initial template. Again, as I said, we found that panning cameras and fast and small moving objects pose a challenge for the. So also this shows the opportunity for the community to improve the performance on this benchmark. Okay, so again, this is the output of the CMFC tracker. I'm not sure if you can see this video, but for static objects, it's doing nothing. But it doesn't need to do anything. For moving objects, it follows them to some extent. Okay.
Ankush, we can always see the videos. Don't worry.
Okay, great.
By the way, 3-4 minutes to go.
Yes. Okay, so there's an interesting subset of tasks that we created around this idea of object tracking, which was with object permanence, which probes object permanence explicitly. So what we did was collected about 600 videos of this thing we're calling cup games. So in cup games, what you do is there's some occluding objects, which are usually some cups or some containers, which are basically of the same shape and size, mostly, but not always. And they occlude a smaller object, then they're shuffled, and then the task for the tracker is to track the occluded object throughout this track. So the reason we chose to do this was in the other sort of standard videos, the occlusion frequency or the occlusions may not be that extreme, whereas here, the target object gets occluded completely, and that poses a significant challenge for the trackers. Also, it's testing for this object permanence, that whether our algorithm can have this understanding that the object shouldn't magically disappear. And also, if the occluding objects are identical, that poses a significant challenge, because you can imagine the tracker switching IDs between different objects quite easily. So we have different grades of difficulties of this task. So if you use identical cups, as I said, that becomes quite challenging. So we have about 480 such videos, and then to make the task slightly easier, we have about 113 videos with transparent cups. So in transparent cups, you can actually see the occluded objects. Then again, we have some gradations in the number of different shuffling cups that we use. So with more cups, it becomes more challenging. The tracking task becomes more challenging. Okay, so here's an example from the subset of tasks. So here you see some transparent cups, and this is one of the this is on the easier side, because you can see the occluded object, and hopefully the algorithm has an easier job of tracking this. In this video, the occluding cups are semi-transparent, so it's like slightly more difficult. Also, the number of objects, number of cups is smaller, so maybe that makes it easier. Here, the occluding objects are opaque and identical, but there's no shuffling, so there's only a distractor action. As you can see, the person plays with the fork in the middle. So in total, all of these videos define various gradations, various degrees of difficulty of tracking tasks, and we present an opportunity for people to have a fine-grained analysis of their trackers using this cup games task. The one thing to note is that in the standard tracking tasks, we don't provide any visibility or occlusion flag for the boxes, but here we do. And that flag basically tells you whether the occluded the small object, in which frames is it visible or not. And we use that to define our metric. So as in contrast to the previous standard tracking task where you're using average IOU, here we use just the intersection over the area of the predicted box, because in order to factor in for the fact that we don't know the precise location once the object gets occluded inside the bigger object. So that's a slight change from the standard object tracking task, but otherwise the metric is very similar. And we hope that this subset will spur research into tracking and also like finer grained analysis of various tracking methods. That's it from my side on object tracking. And up next is discussion by Yi and Carl on points and point annotations, which present an opportunity for more spatially precise tracking with a benchmark. Thank you.
Hello, everyone. I'm Yi, presenting the point tracking dataset part for perception test. Although object tracking captures the general motion of objects in the scene, tracking fine-grained motion of bodies and surfaces, including deformation, is essential for understanding the physics of the world. Although dense surface tracking works well for some categories, such as human, face, and hands, the more general problem of tracking arbitrary points is still unclear whether it is solved or not. Our long-term goal is to track points on any solid surface in the real-world videos, potentially over a long time horizon, because we think this gives clues about the physical property of the objects. And today, however, it is very difficult to measure the progress in this space. Therefore, we introduce a new task called TAP, tracking any point. Given a video and an input query point on any physical surface, we expect the algorithm to track the point when it is visible in the rest of the frames and indicate which frame when it is occluded. And in our work, we aim to build a benchmark for point tracking across a broad range of real-world videos. This means manually label a diverse pool of videos in the wild. We start with the popular Davis dataset and continue annotate over 1,000 videos. We develop a novel labeling pipeline which reduces the annotation effort, and then annotate points with multiple rounds of manual checking and correction to ensure accuracy. We begin with the interface, which allows annotators to choose an initial point and then specify the location on other frames. On the rapid motion, it is prohibitive to require the annotators to pick points on every single frame. Thus, one of our key contributions is the annotation assistance algorithm that automatically allows object motion to interpolate the results in the middle of the frames and reduce the number of points an annotator needs to click. We first use Raft to estimate the short-term motion in the videos based on optical flow. We then ask our annotators to choose the starting point and the end point of a point trajectory. Naive linear interpolation between the starting point and the end point will miss, for example, the camera shakes. Therefore, we instead choose the path which minimizes the discrepancy with optical flow while also going through these chosen points. And we find this optimal path can be efficiently computed using dynamic programming. Here, we compare the annotations without optical flow interpolation and with optical flow interpolation. We show the left-hand side without optical flow interpolation. And you can see that the points drift visibly. But with the optical flow interpolation on the right-hand side, you can see the points are now attached to the swan. Also, with optical flow interpolation, the annotation is much faster. It only requires 2/3 of the time to finish the same trajectory. And based on the annotation platform, we annotate a validation set of the popular Davis dataset. And we see multiple challenge tracking scenarios in the Davis dataset, but mainly typically with the smooth motion. We then manually annotate points on over 1,000 kinetics videos under the 25 FPS and sampled across many different action categories with no constraints on image contents. They may contain, for example, viewpoint changes, heavy occlusions, camera shakes, or cuts. And we annotate on average 26 points per video across 10 seconds. Each video takes up to 2 annotated hours. And finally, we annotate over 100 videos in perception test dataset. The perception test dataset for point tracking are up to 40 seconds long with objects interactions and occlusions in the videos. We annotate over 3,000 objects and over 8,000 points at the full frame rate. We conduct 2 experiments verifying our point annotation quality. The first one is human agreement. For each query point, we ask 2 different human annotators to do the same point track annotation, and then we measure the percentage of their annotation agreement. We find human agrees most of the time for more than 95% on the occlusion and for more than 92% on location within the 4-pixel threshold. On the next experiment, we ask the human annotator to annotate a query point that generated from a simulated video with known ground truth. We then measure the human annotation accuracy by comparing to the ground truth. Again, we find human can reach to more than 96% on occlusion accuracy, as well as more than 96% on the localization accuracy. Both indicates that our point tracking annotation has a reasonable quality to serve as a benchmark. And in summary, we annotate 3 different point tracking datasets. Our datasets in total covers different aspects of point tracking with more than 40,000 point tracks and 7 million annotated points with occlusion flags. We hope this dataset can enable the measure of physics understanding in the real world. And next, I will hand over to Carl to talk about our baselines on point tracking for perception test.
All right, thanks, Yi. So yeah, for the perception test, we are going to, actually, first of all, can folks hear me talking? Yes. Okay, good. Yeah, so for the perception test, we care about being able to make predictions about point tracks along with all the other annotations that are associated with this data set. Unfortunately, this is not a very well explored problem. So right now we just have a baseline algorithm that only does this single task. And we designed it to be kind of the simplest thing that we could come up with that would do a reasonable job on this task, but I think there's still a lot of room for improvement. So as before, the input is a video plus a query point, which is can be on any frame, on any physical surface, and the algorithm must output the track for the whole video. So as you might expect, the first step for our algorithm, which we call TAPNet, is to apply a convnet. And next slide. So the convnet gives us a 3D feature volume that's typical of video neural networks. And given our query point, we just extract a feature representation for that query point by using bilinear interpolation on the frame where that query point was specified. So this gives us a descriptor of our feature, and then we do a dot product with all of the other features in this big 3D feature volume, which we call it a cost volume following the prior literature on optical flow and other point tracking research. And so this gives us kind of a heat map on every single frame for what are the things that are likely to correspond to this query feature. And so then we post-process this with a CNN separately on every single frame to get a prediction for whether the point is occluded, and if not, what is the expected position. So next slide. Let's zoom in a bit on how we do that final prediction. We start with the single frame from the cost volume, which is the comparisons of the query point to everything on that frame. And then we apply a conv and a ReLU to get another feature map next. Then we have 2 different pathways. The first pathway is for predicting occlusion. So we apply a convolution and a pooling down to a single feature vector. And then we apply a small MLP to get a logit. We get a softmax and a softmax cross entropy to train the occlusion prediction. Next. So for predicting position, it's a little bit more complicated, but still pretty simple. We first apply a conv and then a softmax that operates across space. So that the conv projects us down to a single dimension. So we get a heat map of where the point is likely to correspond to. And then we apply what's called a soft argmax operation, which is familiar from the literature. You begin by taking the argmax position of the heat map, and then you draw a small ball around it. And then you take the average of the positions within that ball, weighted by the softmax heat map, and that gives you the prediction. And so this is something that you can backprop through. It is, of course, not completely continuous, but it turns out that you can backprop through this and train it pretty well. And this also lets you get accuracy that's more precise than the feature grid that you started with. And that's basically the whole network. So The next point is, how exactly do we train this? So we don't have enough data from the real world, right? It's very difficult and painstaking to label this. And so we only get a few points out of every video. And it's just we can't annotate that many videos because it's a lot of effort. But tracking is a low-level property like optical flow. You're sort of trying to find low-level patterns that you can match across different frames. So therefore, you might think that, as in optical flow, using synthetic data might be a good approach to get our training set. So that's exactly what we do. We use the Kubrick dataset, which is a recent dataset produced from Google. It uses bullet physics plus Blender ray traced rendering to get very high quality renderings and reasonably good physics. It contains 24 frame clips with a few objects thrown into a scene. So these are all kind of rigid objects, which is a bit of a out of domain thing. But it also gives us perfect point tracking to a much greater extent than we could expect from human annotators. So that's very useful. And I think it's worth thinking about this a little bit because, as is the theme in a lot of this perception test workshop, we can't really expect that the training data is going to cover every possible situation that we might need to make inferences about. We can't expect that the output distribution is going to match exactly the output distribution that we have in our training data because of biases, for example. And so the algorithms that work well on these problems are going to be the ones that can do kind of dramatic generalization out of domain. And this is absolutely the case in point tracking. We simply don't have the data that we would like to have in order to train. And so if you want to perform well on this problem, you need to be able to transfer very well from simulators or whatever data you do have available to the perception test. And simulators, I think, are kind of a particularly interesting, kind of underexplored method for getting training data, because they do have these kind of inductive bias, they have these biases that are different from the real world, but they still tell us a lot of really useful information about the physical properties of the real world and how the 3D world works. So I'm really interested to see, for this task, simulators are really necessary. So I'm really interested to see how people can use simulators in other ways to improve performance. So next slide. So here I'm going to show some qualitative results. So first of all, these are randomly sampled videos. So nothing cherry picked here. And the query points are always on the first frame, but I'm showing, so the perception test videos tend to be 30 seconds plus long. I'm only going to show a random subclip. So the query points may actually look fairly different from what's being shown in these videos. But you can see that TabNet is generally struggling with this data. There's a lot of jittering, especially on weakly textured surfaces. There's a lot of fabrics and soft materials in this data set, which are not well represented in the training distribution. TabNet doesn't really do quite the right thing near occlusion boundaries. The occluder seems to pollute the features a little bit and make tracking difficult, which is not terribly surprising considering that this algorithm is mostly a bottom-up architecture and has to do segmentation on the bottom-up path. And likewise, it struggles with thin objects. I think it's worth remembering that TabNet operates on a relatively coarse resolution feature grid. And so it has a hard time doing a very precise placement. But of course, these are very large, high resolution videos. So there's difficult computational problems with having higher resolution architectures. You might think that some like optical flow, like inductive biases, that points should move slowly over time would be useful, but algorithms that rely heavily on that will have a hard time dealing with occlusions. So, even though there's problems with what you can see here, the TabNet is still typically better on this task than other things that exist in the literature, like algorithms designed for optical flow or for or for structure for motion kind of rigid object tracking. Next slide. So next, let's talk about how we actually evaluate this quantitatively. And for this, we use a Jacquard score, which is kind of like a temporal intersection over union, which is going to be familiar to people who are working in object tracking. But again, this is a novel task, so this is not exactly the same as what's been used before. So again, a Jacquard score is true positives over true positives plus false negatives. So to give an illustration of what this looks like, imagine this is a ground truth track. The first step is to draw a circle, kind of a threshold around that. Things closer like within this threshold will be considered correct. So if the point is, can you go back? If the point is within this threshold, we consider that to be a true positive. Next. If the point is predicted to be occluded when there's actually a point visible in that frame, then it's going to be a false negative. Next. If there's a prediction that's outside of the threshold, then that's considered to be both a false negative plus a false positive, because it's, we don't have a detection where it's supposed to be and there's a detection somewhere else. And next. And if there's a point predicted on a frame where there is no where there's no ground truth point, that's also considered to be a false positive. So next. All right, so now let's take a look at some actual results. So on the left, I'm showing that Jacquard score that I was talking about on the previous slide. We're comparing to a baseline, which is completely trivial. It just assumes that the query points never move. And you can see that TAPNet is doing, about 10% better. It's not a huge amount better, but it's definitely an improvement. It's doing quite a bit better on, okay, so we can break this Jacquard score down into two different pieces. One is occlusion accuracy, which only looks at the predictions for whether the point is occluded or not. And we just evaluate how often it's correct in terms of the prediction of occlusion. And then we also have a localization accuracy, which is we ignore the prediction for occlusion, and we just assume that the algorithm was always correct about predicting points as unoccluded when they are not occluded. And then we only evaluate whether the point is within the threshold for those frames where the point is not occluded. And you can see that TAPNet is doing quite a bit better on occlusion prediction than the baseline, but actually the margin for localization is not so great. So next slide, let's break this down even further. As with the box tracking, we can break this down into whether the objects are moving or not. And you can see that for occlusion accuracy, it doesn't really matter. Points that are not moving are just as likely as unmoving points, or sorry, points that are not moving are just as likely as moving points to be occluded during the course of the video. And the baseline, again, is completely unaware of this, so unsurprisingly, TAPNet does much better. However, for localization, it turns out that the baseline is outperforming us on static points, which is not surprising. It's doing exactly the right thing for those points, kind of by design. But for points that are moving, and especially for points where the camera itself is moving, so you get larger displacements, this is much harder for the baseline, and TAPNet is doing much better. So I think there's a few things to keep in mind about that. Again, we have a very coarse feature grid for TAPNet, and we kind of have weak inductive biases for objects staying in place. Again, it's mostly bottom up. We get features from two different frames, and then we compare them without really considering what's in between them. So I think both of these are areas where this model can be improved. And another thing is that this kind of points out that we have a fair number of objects that are either static or they stay static for a long time before moving. And this was kind of necessary for this for this benchmark because we wanted to make sure that all relevant objects got marked with boxes, and then we decided we would have points for all of these boxes. So being able to detect that things are not moving and label that and infer that correctly is an important part of this benchmark as is. Something that we may reconsider for future versions, but that's the way it is now. But another thing to keep in mind is that there's a big difference between like 50% performance and 75% performance on this benchmark, because there's quite a few points that are easy, and most algorithms are going to get those pretty quickly. But for the harder objects, for the smaller objects with more rapid motion, I think we still have a long way to go. So next slide. So yeah, just in conclusion, point and surface tracking is kind of underexplored, but it's a useful problem, especially for if you want to understand things about physics, if you want to be able to, say, get robots to manipulate things in scenes. This is a really important task to look at. It's something that's non-trivial to annotate. Track Assist makes it possible, and I think we're really the first to have a data set that hammers this task well. And I think we have a baseline. TabNet with Kubrick seems to perform better than Chance and seems to perform better than other algorithms in the literature, but I think there's still a long way to go. And so I'm looking forward to seeing everyone's algorithms tackling this problem. And that's all for me. So next. Next we're going to hear from Adria to talk about actions and sounds in our perception test.
Thank you. Thank you, Carl, for the introduction. As Carl said, I'm going to basically talk about actions and sounds. And essentially, the presentations that we had before from Ankush, Carl, and Yi were focused on objects in a way. So Ankush talked about boxes, and then Carl and Yi went into how to track the different pixels, which most of them belong to the objects, and essentially this relates to how things move in the video. But so this is, I think, a very important bit of the way we understand videos, but of course we're missing a bit of the higher level, which is what's happening in the video. So I think for actions and sounds, we're gonna get a bit more into like exactly how we get information on. So to motivate this, I would like you to watch this video, and I'm hoping there's gonna be sound. So if there is not, please signal it. So if I ask you to describe this video in a few words, I think one decent description would be there is a person using a hairdryer to dry an orange while moving the orange and a pair of scissors with the other hand. Now, I mean, there could be more other details like the table and so on, but in the previous presentation, what we've seen is basically this. So the objects that are part into this video, but essentially we're missing a big piece of it, which is what's happening. So what we are doing in this section is to fill the gaps and add essentially the actions that are missing into this description. So this is what we did. We went into the 11,000 videos. We essentially segment every single action. We have initial timestamp and end timestamp. So this is kind of the segments. And then we have a class. So we have 60 or 70, I mean, I have the detailed number later, but essentially a few number of classes where we kind of classify this. And finally, most importantly, these actions are tied to the objects. And Kush already went into this, but essentially when something is happening, we know which objects are producing it, which connects with every single previous annotation into the perception test. Now, so that's great. And this is one example of where this happens, where you can see how the actions are annotated, and it's related to the objects that take part of the actors. So there is one putting the board on top of the books, and then the ball kind of running. Now, if we are a video model, ResNet, 3D convolution, or so on, and we are fed frames, what we see is this. So this is great because it enables us to know the objects and how they move and even some of the actions, but there are lots of questions that we cannot answer. For instance, was the hair dryer working or not? I think this is something that we can only answer when we have the sound that is tied to this video. So the other way around is the sound enough to get everything? You probably already figured out that no, it's not, but I'm going to show one example to kind of motivate this idea, where I'm going to play a sound of a different video because this one you've already seen it, and then just try to figure out what you think is happening. But no. So now people can imagine different things that would have happened, like producing this sound, but it's very unlikely that you get to a person actually drawing a pencil on top of their notebook and the other objects in the scene. So essentially, the conclusion here is that we need both. We need the sound that is attached to the videos, and then we need the frames as well. Now, there is a lot of modeling already on audiovisual learning. There is some supervised modeling that essentially tries to use audio as input modality and tries to predict audio classes. I think Joe talked about the perceiver at the beginning. There is also some work on self-supervised learning where audio is used as the self-supervisory signal to learn strong representation without labels. But if we look at the benchmarks, there is a gap. So first, most of the benchmarks involving sounds focused on classification. So there is audio set, BGG sound. All those benchmarks are great, but they are classification benchmarks, which is one task, but it's not the only task. Then some other benchmarks do include more tasks, but most of them are speech-centric. So if you look at Ego4D, it has a few audiovisual tasks that are great. They are about who is talking and who is talking to who and so on, which, I think those are necessary tasks, but there is a gap to be filled here, which is all the sounds that happen in videos and that are necessary to understand what's going on. So essentially, the conclusion here is that we lack sound-centric benchmarks where audio annotations are linked not only to kind of the class of the audio and so on, but also to other task annotations. And finally, I think one very particular feature of the perception test is that we have these questions that involve the video and also involve the sound, which is something that I don't think it's in any other available benchmark. So that's what we did. We annotated sounds, and the way we did it is very similar to how we did in actions. We went over all the sounds, initial timestamp, end timestamps of the box, and then a class of sounds. We distinguish the classes between classes about interactions, about humans, about animals, or about objects. And then all the sound segments are kind of tied to the object. So if you think about all these relations, then it's very easy to link them to actions as well, because we have this kind of path through all the objects that produce things. So same video now, we're going to play it with the annotation so that you can see exactly what type of annotations we have. So there were two sounds, the rolling sound and then the hitting sound. And one thing that we can actually do is we can play it in slow motion. I didn't know how to do this automatically, so I'm going to do this by hand. But basically, the idea is that you can see how no, this idea. Anyway, yeah. So this is a bit slower, and you can see how things start, and then there is the sound, and then the other. So of course, on top of this, we can get the same video and show the actions. So I show one example and could show another, but just for completion, I guess, the action of putting the pencil on top of the book, and then the kind of action of launching the pencil. I think you get a very good idea of what's going on in the video with these sets of annotation. Now we can have other examples, and I guess in interest of time, I will skip this one because I think Ankush already showed this. So in terms of statistics, actions and sounds are annotated at 30 FPS, which is great because it means we have like very, very good resolution in time. We are using the same set of videos for both, which means basically we can connect them quite a lot. And then there are more annotations for sounds, which is almost 140,000, than for actions, which is around 75,000. And I think the reason here is that there is a lot of like very small sound that gets annotated, like background sounds, and then kind of repeated sounds that have like their own annotation, while for actions, I think it's maybe longer and more general. But another thing we can look into is like which objects get involved onto this annotation. So the number of objects for actions and sound is both around 63,000. And I think the reason that it's very similar is that most of the actions involve some sound, although it's probably not exactly the same objects. It's similar enough that they might compensate. Like some background sounds do not have like objects associated, but then some actions are silent as well. So I think it's very nice to see these very high numbers in terms of like connections between objects and sounds, because we can use this as a signal also for our models to understand better what's going on. In terms of classes, this is the log scale of the classes. So the one that we have the most is heating, because there is a lot of like things putting on top of other things. So that's a lot of heating. And then the one that we have less is like animal walking, because there are not that many animals involved in here. And as you can see here, there is interaction and then a lot of object sounds, because there is a lot of objects involved. For actions, things are a bit, there are more action classes, and then essentially the higher end of the histogram is about like putting something on top of something, showing something to the camera. So these things that you see repeatedly. And then if you go into the lower end, you would see a lot of pretending. So there is pretending to do an action, which I think is a very nice class to have, because it evaluates the ability of your model to tell between the someone pretending and someone actually doing the action. But of course, we don't have as many of those that we have for the real action itself. Now, one thing we can do is we can look at the correlation in time between audio and sound, actions and sound. Sorry about the title. And basically, the idea here is that we computed which actions go with which sounds in time, so which happen at the same time. And at the left, you have the full correlation matrix, which is hard to parse. But then I showed a few examples in the right where you have pouring something onto something, and then the fluid sound, which is basically water. You can imagine water pouring, and this sound. The clapping hands go with clapping sound. Lifting something and putting it back goes to hitting, because you hit the object, and then moving something around typically relates to rolling, because you might be rolling something around. So I think this is a very good sanity check to make sure that your annotations are coherent. And even this is not a task that we are focusing on right now. I think it's even a good sanity check for models as well, to make sure that models do predict these things together. So I have a few examples. I know we're short on time, so I'm not going to show all of them, but I think this one is good because it's 30 seconds and it shows the annotations. So basically, you can see how every little sound is annotated here. And then the person goes into basically making a T, and you can see how many sounds are involved on making one T. This is the fluid sound. Of course, there is some background sound as well, which typically is not really very good shown in this type of visualization, but typically it usually is annotated in there. So very similar examples. I'm going to skip it. And then, of course, as I said, there is some background sound, and then this background sound is an issue for models, but also for annotators. So this is one example where the annotation is a bit harder because there is this very loud music. But as you can see, we have everything annotated. So this is the same example before, but with actions. I won't play it all because of time, but the idea is the same. We have everything very detailedly annotated. And essentially, this can be used first to make sure the model understands every single piece, and also to relate between actions and sounds. And this example is just a segue on, I think, the considerations about sounds and actions. So you saw here someone clapping, and if you actually look very closely, you can see how the claps are annotated as different actions. So of course, there are a lot of these situations where it's a bit unclear what to do. And I think after like months working on this, the main thing is to be consistent. I mean, you have to just decide something that you think is the best and go for it. It could not be the best, but at least your data set shows consistency, which is the most important thing. Some issues distinguishing one versus many, as you could see here. The fact that we had hierarchical classes helped, I think, in annotation for audio, like having humans and then animals and then others, then it's easier for annotation. And then, as I said, there is some background sound, but then there is the issue of what do we annotate? Like there are some sounds that are very short, but we decided to just go with everything, and then people can do whatever they want with the annotations. And finally, one very practical trick, I think it's good to annotate the frame number and then the time, because if you want to relate to audio, having the time is very important, especially if there are like variable frame rate encoders, but at the same time, sometimes the frame is very useful. So finally, the task that we will do first with this is doing audio and action detection. So the idea is that we can focus on temporal detection plus classification, and we're considering the action former to do that as our initial baseline. As a conclusion, actions are the basic pieces of video understanding, and sounds are basically necessary for parsing. So we have comprehensive set of annotations for both of those, which is great. And we hope that these annotations will push forward the research on audiovisual learning. So thank you very much. And now I pass it to Viorica to talk about question answering.
Okay, thank you. Okay, let me see if this works. Okay, so yeah, just very briefly, we'll go over the VQA tasks, so the multiple choice video question answering and the grounded video question answering. So I won't go over this. Like, I'm sure people are familiar with the many VQA data sets that exist. Just to say that most of them focus on images, whereas our interest is to look at videos such that we can probe for temporal understanding of also for temporal understanding of a scene of a video. So also differently from existing data sets, our questions are designed by our research team. Whereas in most of the existing data sets, they are collected by crowdsourced participants. So we designed the questions ourselves by types of scripts that we designed to make sure that we have a diverse set of questions and that we have good coverage of the different areas and types of reasoning that we are interested in assessing. And then, so the answers to these questions were provided by crowdsourced participants for each video. We aim to have an unambiguous evaluation in our benchmark. So we chose to use multiple choice question answering over open-ended question answering, and then we focused our effort on obtaining hard distractors, and these were collected either with human raters or because we have the structure in the data set. With videos belonging to the same script, we can use the correct answers from other videos to get the negatives for a video. Each question in the data set has 3 options. So 1 is correct and 2 are distractors. And as metric, we use top 1 accuracy. So a random baseline would obtain a 33% accuracy. So here are some statistics about the questions that we have in the data set. So as I mentioned, I presented in the morning, we have all these different skills in 4 different areas. So memory, abstraction, physics, and semantics. And each question can fall under one of these, under one or more of these skills. So actually, we have in total about 40,000 questions. But here, if you count in the table, we go over that because one question can be counted multiple times. However, for the reasoning type, so each question can be either descriptive, explanatory, predictive, or counterfactual. So here we count uniquely. We assign each question to a single type of reasoning. So we can see that we don't have a perfect balance, but we still have a very good coverage, and as a future work, we'll aim to improve the balance across the different types of questions. So here, as I mentioned the numbers, so we have 132 unique questions in the data set, and then each question can be applied to, I don't know, from 20 videos to 5,000 videos. And then we have the number of instances, so these are more than 38,000 video question pairs, which span almost, I think, the entire data set, yeah, 11,600 videos. So here are some examples of questions, but you've probably also seen in the morning. So yeah, I won't spend much time on this. So in the morning we shared a Google form where you can actually test the different types of questions and videos yourself. And I will now pass over to Antoine to discuss the first baseline that we used for our data set on video question answering.
Yes, thank you, Viorica. So can you hear me?
Yes.
For this baseline, the main baseline for the multiple choice visual question answering task, we use the Flamingo model. So if you are not familiar with Flamingo is a visual language model that can take as input a sequence of interleaved videos and text. And it's particularly adapted for few-shot learning. So here, for instance, we show an example of a task where the model can be adapted to question answering given 3 examples. So you can see in gray, you have a 3 example of images, and you have question and answer that are given for each images. And then at test time, you have like this 3rd image that you see with only a question, and you have the prompt answer. And given that sequence, the model is able to answer the last question given the last image. And basically, we have used the same like paradigm to evaluate this model. So this Flamingo model on few-shot learning for the MC VQA task. Can you go next, please? And just to give you some implementation details, so we have discarded the audio for this particular baseline because Flamingo was not trained with audio. And one of the things to note is that also Flamingo is it can only work with short videos. So we have limited the duration of the ingested video to 30 seconds. Which means that if we are actually having more than 30 seconds at test time, we are actually only taking the middle clip. The frame rate is 1 FPS, so which is the training frame rate for Flamingo. So that's something that that can be bad if we have like very actions that happen very quickly. The resolution is 320 and 320, and we are going to show like 4 and 8 shot result, which means that we're actually not going to fine-tune the model on the training set, but just use 4 or 8 examples per question. Can you go next now? So these are the main results. So we have evaluated the 3 different Flamingo models. So they come by different sizes. So you have 3 billion, 9 billion, and 8 TB, which is the largest one. And for each of them, you have like 4 or 8 shots. And you can see that amongst the 3 models, so basically, obviously, when you have more shots, you get best result in terms of accuracy. But what was the most surprising for us is that actually the best result didn't come with the largest model, the 8TB model, but instead with the 9B model. You can see the top results are actually with the 9B with 8 shots. And that's surprising because if you read the Flamingo original paper, like the 8TB language model is actually significantly better than the 9B. And there were obviously a few tasks where the 9B was performing on par or even better than 8TB. So I would say that this particular task is one example where maybe so far we haven't found a way to scale model where scaling the model will actually lead to always better performance. And for now, I will leave it to Viorica to talk about more baseline.
Okay, thank you. So yeah, just here recapping all the different results with Flamingo, and then with the two other baselines that we considered. So we use this frequency baseline where to have a fair comparison with Flamingo that uses a 4-shot or 8-shot. So basically in the frequency baseline, we considered 4 or 8 examples from the training set. We took the most frequent answer, correct answer from that, and then we use that same answer for the entire validation set. And these are the numbers that you can see here for the frequency baseline. So you can see that in 4-shot or 8-shot, Flamingo 9 billion actually does significantly better than this frequency baseline. And of course, as I mentioned, the 0-shot frequency baseline corresponds to the pure random baseline. So that's at 33%. We also collected the human baseline. So we had 30 participants, half male, half female, with advanced English skills, and each of them received a set of 42 video question and options triplets. And they had available 1 hour to complete the test. But in practice, they didn't need longer than 30 minutes. Important to note, they didn't need any training for running this task. So it can be considered that this was run in a zero-shot regime. And we can see the results that we obtained are very good. So we have 91.4%. And it's not 100% just because some of the videos, because of the camera angle or some particular aspects, they can be more challenging. But we are happy with this result from the human baseline, and we aim to collect a larger in the future. So here, just to show more graphically the comparison between zero-shot human, 8-shot flamingo, and the random baseline. So in black, the dashed black line is a random baseline, and then in blue we have the human baseline, and in red we have 8-shot flamingo. So we can see that flamingo does struggle with counterfactual reasoning. It does better on descriptive, which is to be expected given that most of the existing training data is in these areas mostly, so mostly descriptive type of reasoning. And also in terms of areas, flamingo does struggle more with memory tasks and does better on semantics. And yeah, I think all these are to be expected. So just a few words about the video question answering with grounding. So again, I won't go into any details on this, but this kind of such tasks are useful to make a connection between high-level task interface like language and understanding, like low-level understanding in a video where you want to really ground the language into spatial regions in the image. So most of the existing benchmarks, they again focus on images. And again, as I said, we are interested in getting this detailed understanding in videos. So in our case, the input for this task is again the video, audio, and the text question, and then the output. As output, we have a list of object tracks that represent the answer to that question or task. And for this task, we are using the higher order metric for evaluating multi-object tracking. And just in terms of statistics, so we have 35 unique questions, and in total, there are about 5,800 unique video question pairs over a bit more than 3,000 videos. And here are some examples if they are loading. So for example, at the top left, we have track the hidden object, like in a Cubs game scenario. Then on the right, we have the track the launched object task. Or at the bottom, we have track the objects added to the table while the camera was looking away. So in the interest of time, I will skip this. So you can find the details about this in the paper, like different types of cleaning that we did on the videos and annotations. But I'd like to just say a few words about this because this is important. So as next steps, we plan to set up a challenge server. So this will be done using the Kaggle platform, and we will release the test videos at the same time. And in parallel, we also aim to populate our GitHub repository with baselines and evaluation coding for metrics. And again, very important, we are welcoming collaboration. So please get in touch at our email address if you are interested in contributing to this benchmark.